Hello again. First, I want to change the enumeration I used before for propositions and theorems in order to be consistent with the enumeration in the Bible of the theory written by Henrik Stigdenot. And by proposition 8 and theorem 10, what I wanted to say is the proposition 115 and theorem 116 from this resource, and I will continue to follow the enumeration from this book. And so far we have introduced what is an algebraic function field. This is a finite extension of a rational function with some transcendental x. Indeed, we have also seen that for any transcendental, it has finite extension. And in an algebraic function field, we introduce a spatial structure, which is called a valuation ring. This is a proper subring of F containing K. That means it is a commutative ring one with unity. And valuation rings. And correspondingly, we have also seen that it is a local ring, it has unique maximal ideal, and we introduce its unique maximal ideal, that means places, as O minus its units. And conversely, by proposition 115 or proposition 8 in the previous videos, we may also introduce a discrete valuation ring, for given P, because we can characterize the elements in P as their inverses not in P. And if we say it's statement Q and statement P and Q, by simple logic rules, we can state this equivalence as Z not in P if and only if Z inverse in O, or by replacing Z by Z inverse, we can introduce a valuation ring as a set that contains functions such that their inverses not in P. And this gives us one-to-one correspondence between O and P, valuation rings and places. So that means they will be essentially the same tool to conclude the same results or to work with the same machinery. Moreover, in the previous video, we have also introduced discrete valuation maps after seeing that actually valuation rings are also discrete valuation rings. So that means they are principal ideal domains. So let me continue here. For O, we have seen that these are principal ideal domains, and its maximal ideal, the generator of the maximal ideal, has a spatial name as prime element for P, and every ideal can be represented by generator, and this generator depends on the prime element. Here M denotes an integer. Moreover, we have also seen that every non-zero function has a unique representation as t to the m times u with unit u and integer m. So that means for given place with its prime element, we can introduce discrete valuation maps depending on the powers of the primitive element in their representation. And to see that this is a discrete valuation map is one of your homework, but in 2 minutes I will prove, I only give a proof for this triangle inequality. But now the question, okay, so to see the complete picture, we know the correspondence of valuation rings at places, and we obtain a discrete valuation map. And now the question, for a given discrete valuation map, can we obtain places and correspondingly valuation rings? And the next theorem will be an answer for this question. Indeed, it will be also summary what we have seen so far. As usual, f over k denotes a function field. By the way, this is not quotient of spaces. So for the field extensions, we also use this notation. F over k denotes an algebraic function field. And as I mentioned just a minute ago, for a given place, the map VP defined as here is a discrete valuation map. That means it satisfies 5 axioms of this map. And moreover, the elements of OP satisfies this inequality. And similarly, we can also see that a unit, the valuation of a unit set is 0, and maximal ideal contains an element VP of S strictly bigger than 0. And as a conclusion of this definition, we will see that an element, another element, is a prime element for P. So that means it's a generator of P if and only if VP of X is 1. And conversely, now we can also see that if we fix the discrete valuation map, then the set P, which contains functions with V of Z strictly bigger than 0, gives us a place in F, and its corresponding valuation ring contains functions with V of Z is bigger than or equal to 0. And finally, we will also prove that every valuation ring O is a maximal proper subring of F. Is a maximal proper subring of F. So that means if there is another valuation ring that contains O, this forces this O prime is equal to F. So in the first statement, we want to see that VP is a discrete for given P. VP is a discrete valuation map of F over K, and to see that I only prove it satisfies triangle inequality. So that means VP of X plus Y is bigger than or equal to minimum of VP of X, VP of Y. And to be able to apply the definition of VP, let me represent these elements, these functions, X and Y, in terms of the prime element T. That means I suppose that a function X has valuation N, and the function Y has valuation M. Here, U and V are units. And with the loss of generality, we may suppose that N is bigger than equal to, N is less than or equal to M. And when we write X plus 1 as T to the N times U plus T to the M times V, since N is less than or equal to M, we can take X to the N times U parentheses. And now we want to compute the valuation of V of X plus Y by regarding this equation. Here, note that if we are able to see that this element in O has positive discrete valuation, then we will see that this is bigger than or equal to N, and N actually gives us the minimum of VP of X and VP of Y. If this is unit, we will be fine, but if it is not unit, we need to show more. In other words, what I want to say, if we write X plus Y as T to the N times Z, here Z denotes this term in O. And if Z is 0, then by convention of the valuation of 0, we have infinity. This is obviously bigger than minimum of VP of X and VP of Y. If Z is non-zero function, then we can also write it, we can also represent it uniquely as T to the K times U with unit U. And this allows us to write v of x plus y as v of t to the n times z, that means t to the k times u, t to the n plus k times u, since u is unit, its valuation is 0, and we get the valuation as n plus k. And this is bigger than or equal to n, the minimum of v of x and v of y. Actually, in the next statement, it will be cleared, but here it's worth to mention VP of a prime element is 1 because it can be represented only t to the 1 times 1 when it's unit here. And if u is a unit, its valuation will be 0 because it can be represented only as t to the 0 times u. And by definition of VP, we get 0. So see you in the next video. Bye-bye.